gonna talk about functions. The reason for this is because there was a little topic that we left untouched, which is the idea of the notion of cardinality. And when the sets are finite, then there's really nothing going on, just amount of elements. But what if the sets are infinite? Okay. But to understand cardinality of infinite sets, or at least the basics of it, we need to use the language of functions because we're gonna be dealing with infinity now. Okay. You cannot just count stuff. So well, you will be counting things, but there will be a different notion of count. But anyways, we're going to be using functions as our main tool. Okay, so let's make sure that we understand functions properly. You are already familiar with this notion from at least 2 or 3 of your previous courses. Okay, so this should not be a foreign idea to you at this point. We are just going to formalize what we know. We already know logic, we know sets, so we can now be a little bit more serious about what a function is. Okay, so that's what we're gonna be doing in this section. Okay, so before I define function, I need to give you the notion of a relation. Later on, so we're just gonna define relations right now. Later on, after we do our next exam, we're gonna focus on relations entirely. Okay, so we're gonna take a look more in depth to relations. Anyways, as usual, we start with some definitions to set up the language. So what's a relation? So let's suppose that we have 2 sets. So let A and B be 2 sets. Then I'm going to tell you already what's a formal definition. Then a relation from A to B is just a subset of A plus B. That's all it is, a relation. Okay? In other words, a relation is just a set of ordered pairs. Okay? Where the first element is coming from some set, let's call it A, and the second element is coming from another set, let's call it B. Okay? That's what a relation is. So from A to B is just a subset of the Cartesian product of A and B. So if A comma B is an element in this relation, okay? If A comma B is an element in this relation, we typically say, that A is related to B. Okay? So that's the language that we use when we're talking, but for example, this could be represented pictorially, like for example, I'll just give you a quick example. Imagine that A is a set 1, 2, 3, and B is a set 0, let me say 1, 4, 9, okay? Let me do something more, 16, okay? And then, let's say that our relation R is given by 1, 1, 1, 16, 2, 4, 2, 9. Let's say something like this, okay? Then this is certainly a subset of A cross B. All you have to verify is a set of ordered pairs, and all you have to verify is that the first elements, they are really coming from A, and the second elements, they are really coming from B. That's all you have to make sure. So let's see. Let me put a 3 here just to make it more nicer. Okay, so that's a relation, and then you could visualize relations doing a little picture. Sometimes this helps. Okay, so here we have 1, 2, 3, then 1, 4, 9, 16, and then we draw arrows, right, to say elements from A are related to what elements in B. So for example, 1 is related to 1, 1 is also related to 16, 2 is related to 4, 3 is related to 9. Everybody okay with this? And sometimes this helps, okay? Just looking at this picture is actually sometimes is nicer than looking at just a set of ordered pairs, okay? All this means is whatever this relation is, okay? Elements from A are related to elements in B. That is fine, via these arrows or just by looking at the set of ordered pairs. Any questions? No questions? Okay, so the set A has a name. It's called the domain of the relation. And the set B has a name. It's called the codomain of the relation. So A is called the domain of the relation, and B is called the codomain of the relation. Okay, so these are definitions. So the domain of a relation is the first set, where you're getting your elements in the first elements that you put in your order pair, position number 1. And the codomain is a set from which you take elements to fill in the second spot in your order pair. Okay, that's what the codomain is. So, domain, codomain. Okay. All right. Questions? Okay, so we will come back to relations later. Right now, you have a basic idea of what a relation is, so let's define what's a function. What's a function? A function is just a special type of relation. Okay, what type of relation? Well, a relation in which this kind of stuff that's happening here doesn't happen. You see, here we have this one, and this one is related to 2 elements. It's related to 1, but it's also related to 16. Function does not allow this. Okay, if you want a relation to be a function, it has to have a particular property. What is it? That for every input, there is a unique output. Okay, you cannot have the same input going to 2 different places. The same input or the same element in the domain cannot be related to 2 different elements in the codomain. Does that make sense? All right, so let's define this. The definition. This is the notion of function. So a function from A, okay, so let A and B be 2 sets. Then a function from A to B is a relation from A to B such that, so I'm going to first write in words and then we're going to use formal symbols, okay? So a function from A to B is a relation from A to B such that every element in A, so, and this is something else, a relation, to have a relation is just a subset of the Cartesian product. So you don't really even need to, for example, I could just scratch this out from here, meaning this arrow is not going to be there, and it's still a relation. In other words, you don't have to use up everybody from A, okay? Now, for a function, everybody from A needs to be used up, okay? It's not whatever relation you want. First of all, every element in the domain has to have somebody that's related to. That's the first thing, okay? A relation does not necessarily has that, okay? Let me actually do the example that way without the 3 9. So you see that relation is a more general notion of a function. Okay, so a function from A to B is a relation from A to B such that every element in A, is related to only one element in B. Okay? In other words, every element in the domain has to be related to somebody in the codomain. Do you understand this? That's what a function is. Now let's write it, with our fancy symbols from logic and so on. Okay? So notation. We typically use lowercase letters for functions, and the typical letters are F, G, H. Then if you need to work with more than 3 functions, then you start introducing other letters, okay? So we typically, I say typically because, nobody stops you from using other letters and lower and capital letters and so on. So we typically use lowercase letters to represent functions. And the typical ones are F, G, H, and so on. Okay, but these are the ones that we try to use first. Also, something else. This is super important. If you don't know what A and B are, then the function is meaningless. The function that you used to work in college algebra, pre-calculus, and calculus is just f of x equals to some formula, and I never tell you anything else. That's really meaningless. unless there is some special convention or agreement at the beginning. And the agreement in one of those courses is that our A and B are the real numbers, or a subset of the real numbers, okay? But it doesn't have to be. It could be the integers, it could be the rational. It really depends. So if you really want to specify what a function is, you need to tell me what's A and what's B. So the notation that we use is the following. So we write, typically this is how we represent it. So we write F, two dots, then we write A, an arrow, and B. You know, here you put the first set, which is your domain. Here you put your codomain, okay? By looking at this notation, I'm implying that I'm writing a function from A to B. And then, of course, you need to tell me, so we write this, and then specify the root, okay? For example, if there's a 1 here, I need to know what 1 is related to what, okay? So what's the output of 1? That's how we call it. Now remember, this guy here, this set is the domain, and this one here is the codomain. Okay, so that's the formal notation. And another notation is, which is what you all learn in college algebra, the function notation. So a function is a relation, right? So if A comma B is an element of this relation, so if A comma B is an element of the function, how do we write this? How do we write this? When you say that A comma B is an element of the function, how do we write this? You know this. You have taken college algebra, you have taken pre-calculus. Many of you have even taken calculus, differential equations. So you know this. How do we write this? F of A equals B, right? We write this as F of A equals B. But you need to understand that all of these things are just different ways of saying the same thing. When you write F of A equals B or F of 1 equals 20, what you're saying is the point 1, 20 or the pair 1, 20 is an element in this relation. Okay? Which graphically, if you think about the graph of the function, it means that point is on the graph. All of that is the same information, different language. Okay? All right, so instead of writing all the pairs, we typically write this. It's called function notation. Okay? We call this function notation. We don't do this for relations. And remember, this element here is coming from the domain, right? And sometimes it's referred to as the input. And this element here is from the codomain, is sometimes being referred to as the output. Okay? Are you okay with this? Again, none of this should be super strange to you. Okay? You have seen this before in maybe in another format, but we're just putting some formality to this. Okay, so now that we know how to represent functions with this convention, let's write down the formal definition. So formally, is 1 or 2 L's? 2 L's? Okay, so formally we say that f from A to B is a function if the following happens. So for every element in A, okay, there exists a unique element in B such that f of A equals B. Okay? In other words, for every input, there is only one output. It's basically what we're saying. Okay? First of all, you have to make sure that every element in the domain can be plugged in here. That's what domain is, right? All the values that you're allowed to plug into the function. So every element in the domain, you can always find an output, but there can only be one. Sorry. So there can only be one output. Okay? Now, if you watch the videos, they don't use the uniqueness symbol. They actually break this down into an equivalent form, but they just makes the definition a little bit longer. So this part here there exists a unique B. This part here you can rewrite as follows, such that if, oh, let me not put the word here. So if you have A comma B is in F and A comma C is in F, then what do you need to deduce from here? Remember, this means f of A equals B, this means f of A equals C. So if f of A equals B and f of A equals C, what must happen? You want it to be a function, so what must happen?
C must be.
Then B must be C. Right? So this is, if you watch the video, this is what they do, this is what they write. And if you read the book, this is what you're gonna see. But you can write this more nicely, like this. There's only one B that can be the output of a given A. Another way to say it is that if you have two outputs, then they have to be the same. Okay? For the same A, you have two outputs, they better be the same. That means there is only one. Okay? All right, so you can remove these two parentheses and put this big parenthesis, and it's the same definition. Okay? That's what I'm telling you. This is what you see. The first parenthesis with this second parenthesis, that's what you will see in the book and in the videos. But that's the same as that one. I'd like to stress that there is a unique one. Okay? All right. Any questions? You okay with this? So, for example, the very first example that we have here is not a function. Okay? Now, this is not a function for two reasons. Let's see, what's one reason why it's not a function?
One has two different outputs.
Because one has two different outputs. That's it. It's not a function. Now, can you see another problem? For example, even if I did this, would this be a function? Why? Because 3, if we plug in 3, we don't know what to do. Have to be able to plug in every single element in your domain. What we will do in a situation like this is we say, well, okay, then we just don't write 3. And then our domain is 1, 2 instead of 1, 2, 3. Okay? And then that's fixed. That problem is fixed. Okay? And suppose that that was not an issue. So ignore the 3 for now. It's okay not to cover the entire codomain. Okay? That's fine. But here you need to cover everybody in A. Now here, how would you fix it? 2 has no issue. So what would you do? Well, what we do is one of these two arrows, we get rid of them. One of them. Which one? It depends. That's called restricting the function. And then you make a new function that has the property that you want. Okay? Oh, sorry. Restricting the function is something else. It's when you have, actually, I should have done this like that. Let me put it in there. I mean, when you see the video, then you see all the sequence of these things. But, for example, this is okay for a function. You understand this? It's okay to have two different inputs going towards the same output. That's not a problem. The issue is that one input has to have only one output. I never said that two different inputs cannot go to the same place. Okay? Now, this violates another property, right? The one-to-one or injective property. And if you want to have that property, what we do is we restrict the function. What do we say? Well, if 2 and 3 goes to 4, let's just pick one of them. Like, let's ignore the blue apple, for example. Okay, we will discuss that later. Anyway, this is not a function because one has two different outputs. Okay. Any questions? Okay, so let's see. Now that we know what a function is, let me define something. So we already know what the domain is. We know what the codomain is. Now, there is another terminology that we use, the notion of range. The formal name is the image of a function, but you may be more familiar with the name range of a function. Have you heard the name, the range of a function? The formal name is the image of a function. So the image of f, which you can also say range of f, okay? So what is this? This is going to be a subset of the codomain. So this is here on the output side. And this is going to be the actual outputs that the function produces. Okay? Remember, the function may not cover the entire. For example, imagine the function from R to R, and let's say the function is x squared. F of x equals x squared. Domains are real numbers, right? You can plug in any real number you want. What's the output of this function? So what would be the range or the image of this function? If it's x squared, it just greater than or equal than 0, right? So you will only get 0 or positive stuff. You're gonna mix all the negative numbers. So the output of the function is, all the possible outputs is actually a subset of the entire codomain. We declare that this is from R to R, from the reals to the reals. Okay? So that's called the image or the range of the function. So how do we write it? This is a set. What is this? These are all elements in B. This is also B. These are all the elements in B, the codomain, such that there exists an A in A with f of A equals B. So, all the possible outputs of elements in A. Notice that by the bare definition, this is a subset of B. Okay? The shorthand version of this is just all the elements of the form f of A, such that A is in A. Okay? These two lines are the same, but basically, now here I'm using function notation. You know that if I write f of A, such that A is in A, I'm saying these are all the elements in B that have this form. You understand this? So this is typically how we write it, but the formality, the formal one is this. These are the elements in B, such that there exists an A in A for which f of A equals B. In other words, the elements in B that can be written in this form are the result of doing f of something. All right, so that's called the image of the function. I'm going to be using the word image, not the word range. So we are now more sophisticated, so we can use more fancy words. Okay, so that's the image of a function. Questions? All right, so now let's do an example or a couple of examples. I'm going to give you some functions. First of all, I'm going to show you that functions may appear in different forms and shapes. Okay, I'm going to give you a function, and then you're going to identify what's the domain, what's the codomain. Okay, and then maybe the image. Let's see. Yeah, and then the image. Okay, so sample. For the given function, first of all, okay, so for the given function, so identify the domain, the codomain, and image. All right, so let's see. Number one, I'm gonna give you picture form, 1, 2, 3, then 4, 5, 6, and let's say that this is the function f. Okay, this is the function f, and what it does is 1 goes to 5, 2 goes to 4, and then it goes to 5. That's function f. That's one example. Another example would be f from z to z. Okay, and then typically this is what we write. Okay. So remember, this is boldface C. These are the integers. Okay. This is the symbol that we use for the integers. And then if you use this notation, what's typically what we do is we put a variable here representing, an arbitrary input, and then we put here the formula representing the output of that input. This is essentially the same thing as saying f of x equals x squared. Okay? It's just that if you tell me, again, if you just give me this is meaningless if you don't tell me what the domain and the codomain are. So that's why this notation is better, because you can see what's your domain and what's your codomain. Here we only care about integers. Okay, we don't care about fractions. We don't care about, any real number that's not an integer. All right, so that's that one. Then let's make it more interesting. For example, let's do a little Java example. Okay, so in the homework you should have come across a special type of relation, which is the congruent relation, right? You should have seen problems that already introduced this language to you. When do we say that two numbers are congruent modulus a certain number? Let's say 3 congruent to 9 mod 3. Is this true or false? Let's see, what do we mean by the word congruent mod something? Have you seen this in the homework? I mean, there have been plenty problems with this. When in the proof part, when we did 1.4, there were several proofs that had to do with congruences. To say that two numbers are congruent modulo something is just a fancy way of saying that they have the same remainder when divided by that number. Okay? So for example, 3 has remainder 0 when divided by 3, it's a multiple of 3. 9 has remainder 0 when divided by 3. So that means 3 and 9 are congruent mod 3. Okay? For example, 5 is congruent to 1 mod 2, because the remainder of 5 when divided by 2 is 1. Do you understand this? Okay, so that's a congruence. So let's say that you want to, write a little program that takes two numbers as an input, and then the output is whether they are congruent or not. Okay, modulus a certain number. Let's say mod 7. Okay. So I'm gonna use Java syntax. So I want the output of this function to be a Boolean value, right? True or false. So let's say bool, and then I don't know. Let's say are congruent mod 7. And then this is going to take as an input an integer a, an integer b. Okay? Do a little curly braces. And then all we have to say is we return true if they are congruent mod 7, we return false if they are not. Congruent mod 7 means where they have the same remainder when divided by 7. That's all it means. So we can do this just in one shot. So we just return, there is a, you can figure out the remainder. We just do a. There is this little, when you use the percent symbol, in most programming, well, at least in Java and Python, it's like that. I don't want to speak for all the programming languages out there, but this means what you're asking here is you're doing the integer division of this number with this one, and then you are getting the remainder. Okay? So this will give you the remainder. So this is a number from 0 to 6. When you divide by 7, there are 7 possible remainders. 0, 1, 2, 3, all the way up to 6. Everybody okay with this? So we just return this comparison. So this guy equals this guy. In other words, all you do is compute the remainder here, and return the result of this comparison. If they are equal, it's going to return true. If they are different, it's going to return false. Everybody okay with this? The point is that this is also a function. Okay, and I just did a very simple example, but it could be as complicated as you want. It really depends on the sort of function that you want. For example, think about writing a function that tests whether a number is prime or not. Okay, that's a nice little thing. Or to test whether a number is palindrome or not. A palindromic number is a number that can be written the same left to right or right to left, like 121. Right? You input a number, and then it tells you whether it's a palindromic number or not. And many things you can do. All right, so the point is here you have 3 examples, so go for it. So I want you to tell me what's the domain, what's the range, and what's the image for these functions. Take attendance. Daniela Áviles, Andy Brito, Raúl Campos, Brian Cruz, Miguel Díaz, Brian Echevarría, Anthony Fuentes, Ian German, Talía González, Carlos González, Sebastián González, Alejandro Iscaray, Alfredo Llanes, Say it one more time. Alfredo Llanes. I call your name twice. Edward Mendieta. Mario Núñez. Leonardo Quevedo. Michael Valdez. All right. Okay. Let's see. In here, let's say that this is a function from A to B, right? So the domain will be A, and the codomain will be B, and then I want to know the image. Okay, so what's A? What's the domain? So it's a set 1, 2, and 3. Good. What's the codomain? 4, 5, 6. Good. What's the image? 4 and 5. Good. So again, the image does not have to be the entire codomain. Do you understand this? When that happens, then the function deserves a special name. It's called an onto function, or a surjection, or a surjective function. A function is onto or surjective when the image is the entire codomain, when the outputs of the function cover the entire codomain. Okay? And you actually cover every possible. All right. So, okay, number 2 is more straightforward. What's the domain? What's the domain here? The integers. I mean, it's right here, right? So domain are the integers. Okay, so what's the codomain? The integers. Again, once you use the notation, it's right there. You don't have to really think about it. Domain, codomain are right there. Now, what you have to think about a little bit is the image. What's the image of the function? The non-negative integers. No, it's not the non-negative integers. Okay, good. The perfect squares. For example, 3 is not in the image. It's 3 in the image. So those are the numbers that can be written as something squared, right? So if you want to write it in words, these are what we call, the perfect square, which would be, 0, 1. What will be the next one? What is it? 4, then 9, then let's do one more, then 25, and then hopefully at this point, we say and so on. It's an infinite set. But if you write this down, everybody understand what you mean, right? Now let's be more formal. If you don't want, because maybe there is a crazy sequence out there whose first 6 elements are these, and it's not really the perfect square sequence. Okay, so you have to be careful, because when you say and so on, it means that it should be pretty clear what the next number is. But what if somebody comes up with a nice, some sequence whose first 6 elements are these, but then the next one is not 36, it's something else. So, when in doubt, if you don't say, oh, this is the set of perfect squares, then you need to write it formally. So how do you write it? Well, you basically cheat. In other words, we just use the formula that we have provided. So these are all elements x in z, such that x is a y in c, but I would say, because I'm talking about the output, so these are all y's in z, so that there is 6 and x in z with y equals x squared. In other words, I'm basically saying these are all the integers that can be written as another integer square. Okay, that's basically what I'm saying here. All the perfect squares. That's your image. So we are missing a bunch, right? So this is definitely not an onto function. Okay, questions? Any questions? Okay, about this one. About this one. For example, let's say this function, so R congruent. Let's write it in function notation. R congruent mod 7. How do you write this in function notation? Function notation, I mean, you tell me what's the domain, and you need to tell me what's the codomain, right? So that's what I want to know. I want to know what goes in there for A and what goes for B. So fill in the blanks. What is it?
Integers.
So what do I write?
It'd be a set of integers.
So what do I write? What type of input this function is receiving?
So
How do we talk about two stuff?
pair,
A pair. How do you write pairs?
parentheses.
Those are the elements. So when you have a pair, where is a pair coming from? Where does it come from? What type of set is this? It's a Cartesian product. If you have pairs, you have a Cartesian product. So this takes a pair of integers, so the domain is C cross E, right? And then what's the codomain? It's a set with two values in it. What is it?
True or false.
The value true, the value false. Do you understand this? That's what this is. This is a function whose input is a pair of integers, so it's an element in the Cartesian product C cross C, and the output is either true or false. So it's a set with these two elements. I mean, by T I mean true, and by F I mean false. Or you could say 0, 1, and then say, 0 is false, 1 is true. Okay, let me write this more nicely. Okay, so the moment that we do this, then it's clear what the domain is. What's the domain? The cross product, so it's C cross C, because the same int, right? Here we are specifying it's a pair of integers. And then what's the codomain? The codomain is true false. And then what's the image? What's the image? Is it the same? Why?
It's gonna get true or false.
So can we always get the two values? So to tell me that the image is this, all you have to tell me is give me an example that exhibits true and give me an example that exhibits false, and then we're good to go. Okay? Remember, here we do need some reason. So in this case, the image and the codomain match. Okay, so let's justify. Give me why an example of obtaining true, right?
1, 1.
So 1, 1. Okay, good. So for example, since 1, 1 is an let's see, since 1, 1 gives, it's just that, okay, 1, 1, I'm gonna write like this. So gives true, okay? Because 1, of course, has the same remainder as 1 when divided by 7. In this case, the remainder is, what's the remainder of 1 divided by 7? 1, okay? Good. So 1, 1, it gives you true. So this is another way that we write, for example, when you write f of a equals b, if we have all of this business, we will write like this: a goes to b, okay? And we can write it that way. Okay. Because I don't want to write all that big name for the function again, so just gonna say since 1, 1 give me true. Now we need to exhibit something that gives me false, and then this way we exhibit. Good. 1, 2. Why does the pair 1, 2 gives me false? Because the remainder of 1 divided by 7 is 1, the remainder of 2 divided by 7 is 2. They are not equal, so this function is going to return false when you input this pair. Do you understand this? Yes? Okay, so there you go. All right, questions? Any questions on the notion of domain, codomain, and image? No? Okay, perfect. So let's see. Should I go more? I guess I should say here, let's rewrite all of that mathematically. So this sentence, let's write it. So we already have this part right here, just to, and now how do we just need to specify the rule. Remember, if we write this, we need to somehow say the rule. So a comma b, so where does it go to? Well, typically what we do is, in this case, this is a piecewise function. It depends. So if a is congruent to B mod 7, this is how we write it in math, okay? That's how you write congruent. This is the symbol for congruent. Here we're saying A is congruent to B mod 7. So if that's the case, then we output true. And then, of course, we just say otherwise, but if A is not congruent to B mod 7, then we output false. And so right here, I just rewrote that Java code into a formal function notation. Okay. All right. So let's see. We have that. Then, okay, I'm gonna give you one without the pairs, but I don't think you need that. I mean, that's back from college algebra, so we don't need to repeat that. Just want to show you something that you may not be used to. Okay, everybody here has taken programming? Yes? Okay. And if not, you're gonna take it. Otherwise, you wouldn't be taking this course, right? So it's good to see this kind of stuff from time to time. All right. So, any questions about the notion of function? No? Okay. Good. So then, let's go ahead now and talk about a little bit more about image, and now this notion of inverse images of sets. Okay. So we just discussed the notion of the image of a function, but now we can also talk about the image of a set, and also the notion of the inverse image of a set. Okay, so let me define this. Okay, so definition. Let f from A to B be a function. So when I write this down, I'm already implying that there are two sets, set A, set B, and then A is a domain and B is a codomain. Just by writing this, all of this is already in place, okay? I don't have to say let A and B be sets, blah, 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 okay? So we have a function from A to B. Then, now let S be a subset of A, okay? Let S be a subset of A, and T be a subset of B, okay? So I'm going to define two things. Number one, for elements, for subsets of A, we can talk about the image of those, of that set. And, it will be hopefully what you think about. So the image of a function is just all possible outputs. The image of a set is all possible outputs when you take elements from within that set, okay? So then the image of S, sometimes we just write this, okay? This is the collection of elements of the form f of A such that A is coming from S, okay? So these are outputs of the function, just collect the outputs of the function, but in such a way that the inputs are coming from the set S, not outside of S. Remember, S is a subset of A, so that's okay. So that's the image of S. This is a subset of what? Who can tell me? This is a subset of what? Of B, right? This is a subset of B. The elements here are these guys. What are these guys? These are outputs. And the outputs live where? B. Yes? So the image of a set is this. Now, also you can play the game backwards. Sometimes you have elements in B, and you want to ask, are these guys coming from somebody in A? Are these the image or the output of some input? Okay? So sometimes you want to ask that question. That's what we call the inverse image of a set. So number two, the inverse image of S, of T, is going to be, okay, so we do have a notation for that. So the image of S actually, sorry, I mean, you can use that notation, but this is the one that we use typically. This is more suggestive. So let me stick to that. But now this is a set. So you need to understand that this is a set, and what I mean by this is doing f of every little element in S, and then you collect that. That's exactly this. Okay? This is more understandable. Now the inverse image of a set, the notation is, as you probably expect, we use the inverse function notation, but it's not a function. Okay. So the inverse image of T, this is how we write it. So what is this? These are elements in A, so that when you apply the function, they go to T. Okay. So these are the elements in A, such that when you do f of A, that belongs to T. This is a subset of what? This is a subset of A. Okay? So you can use this image operation, if you will, to push subsets of A to obtain a subset of B, and then you can use this inverse image operation to take a subset of B and bring it back to A. Okay? So then another question is, if you push a set and then you bring it back, does that mean that you're gonna recover the entire set? That's one question. Okay. So if I do the image of S and then I do the inverse image of that, so do they cancel each other? Okay. There are many questions now that you can ask. So I guess before I ask those questions, let's do a concrete example. Okay. So let's see. Let's say that we have the set A, which is 1, 2, 3, 4, just to hopefully have this concept more clear. And let's say the set B is 20, 30, 40, and 2022. Okay, so I'm gonna define the function via a little picture. And then there's 20, 30, 40, 20, 22, and then we have our function f, and this is what it does. So it sends 1 to 20, it sends 2 to 30, it sends 3 to 20, and it says 4 to 20, 22. This is a function f, okay? Now I'm gonna ask you some questions. So first find f of a, then find f of 1, 3. So by this I mean this is the image notation, okay? The image of this set, the image of this set, okay? Find the image of those set. Then let's do the inverse image of B. Then let's do the inverse image of the singleton 20. Which, when we write it like this, sometimes you will see people writing this, okay? But technically, it's really the set containing 20, okay? Then E, let's do the inverse image of 20, 22, and 40. And F, let's do the inverse image of 40. And of course, this question cannot be missed. It has to be here. What is the image of the empty set? And what's the inverse image of the empty set? Right? So, empty set is a subset of every set. So, I can ask you, what's the image of the empty set and what's the inverse image of the empty set? All right, so let's see. Let's answer these things. And hopefully then these ideas of image, inverse image, they stick, okay? So again, we kind of use the same function, similar to the function notation for the image. And the reason is because this suggests the definition. If you see this and this is a set, all I'm telling you is, okay, this is a subset of B because we're going to B. And what is it? Or elements of this form. Just do f of whatever is in here and you collect those in a set. Okay? That's basically what we're doing. Of possible outputs of the elements of S. That's what it is. Now, for the inverse image, it's different. This is back, you have a subset of B, and then you're looking back in A, and you're seeing everybody in A that when you apply the function goes into T. And you take those elements, and that's what we call the inverse image, okay? So all the pre-images of the elements in T. That's called the elements back in A are called a pre-image. For example, 1 is a pre-image of 20. 3 is a pre-image of 20. Okay? 20 is the image of 1 and 3, and now 1 is a pre-image of 20. Okay? All right, let's see. Image of A. What is this?
20,
So that would be 20, 30, 20, 22. Does everyone understand this? Remember, it's all possible outputs of elements of A. Now, in this case, A happens to be what? It's the domain of the function, right? So the image of the domain is just the image of the function or the range of the function, okay? This is just the same thing as the image of the function. Notice how we are skipping 40. Why are we skipping 40? Because nobody gives you 40, right? These are all possible outputs of elements of A. Here they are. Let's see. What's the image of 1, 3? 20. Very good. So everyone understand this? You just connect f of 1, f of 3. It happens that they both are 20, so it's 20. Okay? What's the inverse image of B? So that is, again, all elements in A, so that when you apply the function, it goes to B. So what would that be? 1, 2, 3, 4, right? It's all of A. It's right here, A. In other words, the inverse image of the codomain is always the entire domain, right? Because every element in the domain goes towards the codomain. So the inverse image of the codomain is the entire domain. Okay, now it's more interesting when you get subsets of this. All right, what's the inverse image of 20? Okay, so it's 1 and 3. Again, the elements in A, so when I apply the function, they go into that set. In this case, they give me 20, right? That's what you are recollecting. So it's 1 and 3. All right, here. 4. What is this? 4. Very good. So the image, the elements in A, so when I apply the function, give me either 2022 or 40. Okay? Okay, 4 goes to 2022. Now to 40, nobody goes. Okay, then we don't write anything. Do you understand this? Okay. So how about F? It's empty. Why? Because there is no element that goes to 40. Do you understand this? Remember, the question that you are asking here is, the elements here are elements in A, so when I do f of that element, gives me 40. Well, if there is no element with that property, then this is just the empty set. Yes? So, what's the image of the empty set? Why 40? Remember, what is this? This is supposed to be elements of the form f of something coming from here. Do we have anything here? So, can we do f of something? So what is this? The empty set. Regardless of the function that you have, the image of the empty set is just the empty set. If you tell me something else, you're telling me that that element is the result of doing f of something from here. Okay? Violating the fact that it's the empty set. And so how about this? What's the inverse image of the empty set? So this will be, remember, these are elements in A, so when I do f of that, they go to the empty set. Well, the empty set has no element, right? So the inverse image of the empty set is the empty set. Yes?
Is there anything that will give you 40?
Say that again?
Is there anything that will give you 40?
That will give you 40. No, because 40, I mean, if you think about it, the function itself has no information on 40. Okay, 40 happens to be part of B, but f itself doesn't see 40 at all. It doesn't see 40. Remember, function is a rule. And just the elements, it tells you for every element in the domain what it gives you, okay? And then you collect that, and that if that's inside any other bigger set, that's the codomain. But really, the function, the only thing that it says is the image, the range. That's the only thing. That's the only thing that the function sees. Anything else is it misses. Okay. All right. Questions? But I can ask this type of question because here I'm in the codomain. This is a subset of the codomain, so I have the right to ask you this. Now you need to tell me, no, the function doesn't know anything about it, and you tell me that by writing the empty set. Okay. Yes.
Can you ask what the image of B?
No, because by definition, so that's a good question. By definition, when you say the image of something, this something is coming from where? It's a subset of A. So just think about it this way. A function is, you have elements in A relating with elements in B. So if you have some stuff here, and then what you can do is you can push it forward and then ask what happens to this element. That's what image does. That would be the image of, those things. Now, sometimes you have something going on over here, and then you're wondering, okay, this guy is coming from what? You know, these elements in here, where are they coming from? In A. So if you want to return back to the domain, that's what inverse image does. So if you remember from your college algebra class, the notion of inverse, what's the notion of the inverse of a function? The function has to be special, but once it's special, it has an inverse. What's the inverse? It's the opposite, right? The job of the inverse is to undo what the function does. If the function says 1 to 3, the inverse has to take 3 and send it back to 1, right? To undo the function. So the inverse is something that you take an element from here and then you ask what's on this side. So the image takes you from A to B, like the subset of A, and gives you a subset of B. The inverse image takes a subset of B and gives you a subset of A. Okay? So asking what's the image of B, it doesn't make sense. You put that and then you're going to get a compiler error. It's not going to even compile your program because it doesn't understand. We don't understand what that is. Image, it has to come from here. Inverse image, it has to come from here. Inverse image is to go back. Image is to go forward. That's why we write the arrows and so on. So we have a clear understanding of directions, how we go. Okay? Good. So next time we're gonna, there are questions. Like for example, if you have two subsets of A and you look at the union, right? That's a subset of A. So you could talk about the image of the union. The question is the union, is the image of the union of the images? That's one question. Okay? So some questions remains to answer. For example, let's say S and T are subsets of A. Then the question is, I can look at the image of S, I can look at the image of T, and I can look at the image of the union. Remember, the union is still a subset of A, right? Then the question is, what happens here? Are these two things equal? Or maybe your subset? Which one of the two is it? Or maybe the two, okay? And of course, similarly with intersection, the same question. And then similarly with inverse image, okay? So those are the things that we're going to explore next time as well. And you're going to see that the inverse image actually is a nicer operation. Image is not so nice. When you do image, you forget stuff, okay? Because if you think about it, if you do image, you're going to be on this side, and then you kind of, once you're on this side, you kind of forget that 40 is not coming from anything in A, because you're already here. And when you're here, you see all of these guys and say, oh, 40, you're my friend. But that 40 is a spy. It's not coming from anybody. Okay? So image, you sometimes lose information. Inverse image is a more friendly operation. Okay? But we're going to explore that onwards.